to introduce Professor Rich Sutton. Like many of you, he's been a huge influence on my work, both indirectly and directly with the comments and help he's given over the years. I'm not going to go through his bio because it's extremely intimidating. But if you are interested, it's definitely a good read. It's clear that Rich has had a huge influence on our field. So today I'm really excited to introduce him, and he's going to be talking about the increasing role of sensory motor experience in artificial intelligence. So with that, I'll hand it over to Rich.
Thank you very much, Matt. Hey, first though, I want to tell you about an exciting event that's going to be happening in Edmonton. It's AI Week, Amy's AI Week, 4 days in May. We're going to get together and inviting you to join us for these 4 days of workshops and science and social events and educational events. Get you to see the ecosystem, and we'd like to meet you and talk about it all. And if to help you come, there's some funding available for travel expenses, and you can find out more about that by consulting this link at the bottom, aiweek.ca, talent bursaries. Okay. Now, let's get going with the talk, Increasing Role of Sensory Motor Experience in AI. This is a talk where we're not going to present you any new algorithms, but I'm going to sort of step back and try to get some perspective on the field of AI. Whenever we do this, it's important to see where the field is and what the history of it's been in order to figure out where we should be going. And to see, often I talk about the idea of trying to see the obvious. And this is a case where we're trying to see the obvious development, the natural development of our field, and how sensory motor experience has been playing a larger and larger role. So let me be clear, what is this sensory motor experience? I just mean the ordinary sensations and actions that you get interacting with the world. So here's our agent. It receives some data from the world, sensations, and it sends some data out to the world, some actions. And that's exactly what I mean by experience. So reinforcement learning obviously involves this experience, and prediction learning involves this experience. But supervised learning really doesn't involve experience in this sense. It has special training data which will not be available during the ordinary interaction. Now, this experience is the agent's only access to the world, and it only has its meaning by relationships to other bits of experience, with one exception. Perhaps one exception is the reward. It's a bit of sensation, which has a special meaning that it's good. But otherwise, there's no special meaning. It's just data. The agent has to make meaning out of it. So this talk, I want to ask this question. Sincerely ask this question: will intelligence ultimately be understood, explained in terms of these experiential terms like sensations, actions, and reward, time steps, these things that are inside the agent? Or will it be described as it has traditionally been described, in terms of things external to the agent, objective terms, things like states of the world, objects, people, places, motion, space, distances, all these things outside the agent? So that's the question that I want us to kind of riff on, because traditionally we have thought about what intelligence does as understanding the world in external terms, and there's just been gradually a shift towards experiential terms. And this talk will go through 4 steps in that progression over the long history of AI. And we'll see this slide a couple times as it's sort of the outline also of the talk. I'll go through these 4 steps: agenthood, having experience; reward, which is having goals in terms of experience; and then having state, the state of the world and knowledge about the world also being represented in terms of experience. And for each one of these steps, throughout the history of AI has reluctantly moved towards experience. It's always started at thinking in terms of more objective terms, and has reluctantly and begrudgingly moved towards experience. And it has done this in order to be more learnable and grounded and scalable. So that's what I want to communicate today. So let's get started. What's this? The first step is agenthood. Agenthood just means having experience, having an interaction, having a life, having sensations and action. And we should just note that this is a new thing. It hasn't always been this way in AI. In the early years of AI, the first 30 years, 35 years, there was very rare was there to have experience at all, because there was no agents. So most AI systems were problem solvers and question answerers, and they had no sensations or actions. A little bit of robotics, that's sort of an exception, but mostly they were things like problem solving. A typical problem was a start state and a goal, and operators were defined. The operators were not actions, but they were state transitions that you could choose to make as an AI agent. And the solution was a sequence of operators that were guaranteed to take the system from start to goal. And there was no sensing or acting. The operators were deterministic, so they never actually had to execute the solution once they found it, because they knew that it would deterministically achieve the result, and so they didn't have to sense, no sensing. And then say once you had the solution, it was never actually done, because there was nothing. It had to happen as it was modeled, and so you didn't actually have to do it. Another way of assessing it is you look at early AI textbooks. This is from a textbook by Niels Nilsson in 1980, and it would brag, he was a textbook author, and as we do, we have to brag about our field a little bit. And so his bragging in his preface would say that AI could do things like these. It could diagnose diseases. It could plan the synthesis of complex organic chemical compounds. It could solve differential equations in symbolic form. It could understand limited amounts of speech and could write computer programs. And all these things were formulated not in a way that didn't involve sensations and action. They were just analysis and diagnosis, and there were no sensations and there were no actions or choices. So for the last 30 years, AI, though, has clearly been focused on agents and building agents. And this happened gradually, but one way of marking it is the first edition of the now standard AI textbook by Russell and Norvig. This is from the 1985 edition, the first edition. And that book did base AI on the agent perspective. And so that was a new thing. It wasn't new really to the field, but it was new to base a textbook on this perspective. So they said in their preface, or their introduction, that the unifying theme of the book is the concept of an intelligent agent. In this view, the problem of AI is to describe and build agents that receive percepts from the environment and perform actions. So they really made it the standard approach. The modern approach was to view this agent-oriented view. Okay, so that's agenthood, having experience, now the standard approach in AI. Let's go on to step 2, reward. This is to think of the goals of the AI agent in terms of experience. That too is sort of new, but it's now become a strong point of view. It's associated with reinforcement learning, but it's more widely used. So then what is the strong view? It's that there's a single number that you receive over time called the reward. You receive it from the world, so it's part of experience, part of your sensation. And this is a sufficient way to formulate goals in AI. This has been stated in a strong way recently by David Silver, Sindar Singh, Joanna Prickup, and myself, and the reward is enough hypothesis that intelligence and all of its associated abilities can be understood as subserving the maximization of reward. So that's a strong, clear view that the rewards are enough for a formulation of goals. And I think the normal reaction to this hypothesis is for it to be unsettling, to be uneasy with it, because still for many, reward does not seem like it's enough. And so I want us to acknowledge that here. The point of this talk is both to see the progression towards experience, but also sympathize and understand why experience is something that we reluctantly base our AI systems on. So reward doesn't seem like it's enough because, maybe it's enough for animals or enough for engineering, but it's not enough for people. It's not enough for humans, for our goals. Just the whole idea of a single number from outside the mind, it just seems too small and too reductive. And in fact, even too demeaning, because surely people's goals are grander. We want to raise a family or to save the planet or to contribute to world peace, make the world a better place. So surely our goals are greater than just maximizing our pleasure and comforts. This is a normal reaction, which we can understand. And yet, we come around and more AI is using reward. So it's still uneasy with it. So if you go back to that Russell and Norvig, the textbook, their latest edition would define the goal of the AI as world states to reach, so external objective terms. Of course, there are also chapters on reinforcement learning where they use reinforcement learning and they use reward. But we're uneasy with it. Now, with the rise of machine learning and AI, the reward formulation is becoming more standard. So it's now a standard way to think about planning. It's Markov decision processes. And like even critics of reinforcement learning, I think Jan LeCun would describe reward as, and reinforcement learning as the cherry on top of the cake of intelligence, recognizing that it does have a prominent role in the goals of the intelligence. And here's another example of reward becoming more important. This is in the Soar architecture. The Soar cognitive architecture, it's classic, good old-fashioned AI from the 1980s and has production rules and symbols. But since 2008, it's included reinforcement learning and reward as part of the formulation of the problem. So we point to this little box here, which is part of Soar, which has all these other things like working memories and long-term memories, semantic and procedural. But it also has reinforcement learning and rewards. Okay, so that was step 2. More and more AI is starting to have its goals in terms of experience as a reward signal, a numerical reward signal received from the world. And these two steps, these first two steps, steps 1 and 2, are sort of past, and steps 3 and 4 are a little bit more looking to the future. And so before I go to start looking at the future, I want to take a little interlude and just talk some more about experience and what it is. So let's do this interlude and just look at experience. So here's some experience. It's a concrete example, but it's imaginary data. So we receive some signals, maybe some bits from the world, maybe some signals that are not binary, but have other values like 3 and 2. And also there are some signals that we send to the world, some actions. This happens at a particular time. We can also have signals that we receive from the world that are continuous, like the reward, which is a numerical signal. It's not symbolic. And this happens over and over again through time. So over time, it would look more like this, where we receive a dense sequence of sensations and actions. And I want you to think of the time step as being small, like maybe 1/10 of a second. And so we, the agent, are sitting at the most recent time step here. It's time step 7, and we're trying to decide what's going to happen next or what we should do next. Now, even as you look at this, it seems detailed and small and specific and, not exactly intuitive. And so I want to try to make it a little bit easier to deal with. And so let's take, now that you understand what's going on, these bits going in and out and the signals going in and out, let's reduce them to something more visual. So let's reduce them to colors. The the zeros and ones become white and gray, and the 4 valued signals become 4 different colors. Similarly for actions are reduced ones and zeros to whites and grays. And then the continuous value is represented by this bar chart, and where the sign is represented by the color and the magnitude is represented by how big the bar is. Okay, so this is the data. And so what is the job of the AI agent? The AI agent is to find patterns in this data. And like you are intelligent agents, so you can find patterns. So, you know, if you look at this data, do you see any patterns in it? And because there are simple patterns here that you might be able to pick out. The most prominent one, I'm sure you'd see it if you looked at it for a while, is to look at the relationship of the actions and the first sensory signal. So here, the first sensory signal is white, and the last action is white, and the first component of the sensation is white, and that carries through all the steps. So if you as the agent were to see this, you might think, well, the third component of my action causes the first component of sensation to have a particular value. And so that's the kind of, a simple example of the kind of thing that the agent looks for and constitutes the agent's understanding of the world. It understands that it has these sort of relationships. So let's look at some more. So there's another one, which we can only see 2 examples, but here we have the 5th signal is red, and following that, the 6th signal is green. And this happens twice, and maybe it just happens by chance. And this data, as I said, I wrote a program and made it up, and it's not from any real system, but it does show you the kind of thing that's going on. Now, when you see this semblance of a pattern, red followed by green on the next time step, you might say, well, that could be just chance, or maybe it's a reliable effect. We need more data. So let's get some more data. Let's play this out forward into the future. And we see a lot more data. And the first 2 examples of the red followed by green are shown there. And if we were to look at the rest of this data, we'd see that it is reliably played out throughout the data, as whenever the 5th position is red, the next time step, the 6th position is green. Now let's do one more example. It's also true that after this pattern of red then green, 2 steps later, there's a blue pixel. And that follows once, twice, and in fact, every time. So that's a fact about this world. It's a predictive fact. And it's the kind of patterns that I see intelligence as discovering, except, of course, these are really simple patterns. The patterns that are important for our lives are more complicated, but they're not a difference in kind, they're just a difference in complexity. Okay, so let's sort of summarize what we've seen, clear that out. We've seen that different sensory signals can be qualitatively different from each other. So the action signals are action. Well, no, different sensory signals can be qualitatively different from each other. So look at the sensory signals. The first 4 are binary. The last 7 have 4 values. So those are a qualitative difference between the signals. And the last signal is continuous. So it has different range of values. And then the predictive relationships, we've seen them. We can see the actions can be related to sensations. The sensations can be related to each other. And there are short and long-term patterns in these data. Yeah. Before I go on, there's actually another pattern. There's another pattern that I've put into this data, and you might be able to see it if you look at it for a moment. Yeah, I invite you to look at this data And look at, I don't know, we've talked about the fifth signal and the sixth signal. What about the last few signals? Do you see any patterns in the last few signals? Well, if you do, you could call it out. But let me, you notice, like here, there's a whole bunch of reds in a row. Here, there's a bunch of yellows in a row. Here's a bunch of yellows, here's a bunch of greens. And this plays out, like here's a bunch of reds. These last three signals are kind of sticky. Once they get to a color, they tend to stay on that color for a while. Lots of greens. So this is a qualitative, this is a relationship between a signal to itself. If it's been one color for a little while, it tends to stay that way. Well, that's another pattern in the data. Okay, so all these patterns that we've looked at are about, what the sensory signals will be at a particular point in time. But that, and often when we say prediction, we say, oh, I'm predicting what some signal will be at a time. But that's really a very small sense of prediction. There are much more, many more possibilities. And one of these possibilities is familiar to many of us because it's the most important prediction in reinforcement learning. And that's when we learn the value function. We learn to predict, we say we learn to predict reward, but we're not predicting what the reward will be at a particular time. We're predicting how much reward do we expect to get generally over a period of time? Like how much reward do we expect over the discounted future? So this is a prediction, but it's not of a data signal. It's not of a particular data signal. It's a prediction of the sum of future rewards. So you never actually see the reward and compare your prediction directly to the reward. You make a temporal difference error and so forth. So let me show you what the return is, what the sum of the future rewards are at each point in time, because that's what we would like to predict, one thing that we would like to predict. So I'm drawing it as an additional column. The return is the sum of the future rewards. So look, here are the rewards. Like here's a time when there's a lot of rewards. And you notice that the return is large just prior to those rewards. And if you had a time when there were negative rewards, then the return will be large prior to those negative rewards. In fact, what the prediction is, like at this time step, this bar is green and large, the return means that the sum of the future rewards weighted by some exponential discount factor is large. And then over time, this kind of slides along and we can see, so here, there, the rewards are slightly negative coming up to the future. And if we slide, and so we maintain this as we move along. Here's when the rewards coming up are large. And here again, it's where the rewards coming up are negative, largely negative. So this is something we'd like to predict, but it's not the prediction of a particular sensory signal at a particular time. It's a prediction of a combination of a function of the future. So this is generally true, that the most important predictions are functions of future sensory signals. So value functions are like that, and the general notion of a value function are like that. The general value functions, they can predict not just the reward, but any signal, and they don't have to have an exponential envelope, they can have an arbitrary envelope, and they can be contingent on a policy. And this gives them much greater flexibility, and we can say a lot more about the world. Okay, so, but they're not arbitrarily flexible. We can't say anything about the world because different ways of different kinds of predictions vary in how easy they are to predict, to learn, and to predict. And so general value functions are constructed so that they're easy to learn, and we have many learning algorithms for learning them. Okay, that's my introduction to experience. Now you know what I think is the job of the AI agent. An experiential AI agent is to figure all that out and be able to predict and control the future. So let's go on to step 3. which is thinking of state in terms of experience. So historically, in AI, state has not been done experientially. It's been done in terms of the external world, objective state. So classically, perception produced symbolic propositions whose truth values were assumed to match the world. So you'd have things like block C is on block A, or John loves Mary. These are statements about the world and not about sensations and action. And more recently, we have probabilistic graphical models, like this one, where we talk about, oh, it's cloudy outside, or the grass is wet, or it's raining, the sprinkler's on. These are explicitly state variables that are aspects of the external world rather than about this agent's sensations and actions. In POMDPs, it's kind of similar. Instead of having, we have the state is called the belief state, and it's a probability distribution over the underlying world states. So all these objective states are far from experience. So what would be the alternative? Well, the alternative to objective state is experiential state, in which the state of the world is defined entirely in terms of experience. So this box gives the definition. Experiential state is a summary of past experience that's useful for predicting and controlling future experience. So just note that in this definition, there's no mention of external entities out there in the world. There's just your experience and what you have to remember about it in order to make good decisions and good predictions about the future. So some modern AI embraces this experiential state. Most commonly, we just build it into our system. So like in the Atari game playing system DQN, they would provide not just the immediate video frame, but the last 4 video frames as part of the summary of the past that they use to predict the future. And they might also include some of the recent but past actions. So that's just building it in. Other approaches try to figure it out, try to create the state. So compression approaches to AI, where they try to compress the data into a compact form that summarizes its past. And of course, basic neural network mechanisms like long short-term memory are experiential states, and also predictive state representations and spectral methods. So all these approaches learn, after the first one, learn or discover their experiential state. Okay, so now I'll just make some observations about experiential state. Really, you want it to be recursively updated. So this sequence is supposed to remind you of the colored sensations and actions that we saw earlier, progressing over time: sensation, action, sensation, action, sensation, action. And the state is a summary of all the previous sensations and actions that you would use then, say, to make a prediction or to choose your next action. And just notice the structure, the flow of information. This is a little awkward. If you really you have to do a state at each moment in time. So there will be a state at each previous moment in time. And you have all these information flows. A much more elegant way to do it is to do it recursively, as suggested by this lattice structure, where each state is constructed from the previous state and from the new information. And then it's a much simpler, more straightforward flow of information. And this leads to an agent design. Let me just show you what that agent design looks like. We have our sensation, which will lead ultimately to action. And we construct the state from itself, from the most recent sensation and from the most recent action. And that's the experiential state. That experiential state then is sent on to the policy, which picks the actions. And it might also be sent out to other predictions we might make, like the value function. And while I've got this kind of state diagram up here, let me just flesh out the rest of the agent, because the rest of the agent maps onto our 4 steps of increasing experience. If we flesh it out a little bit, this does become the value function, so it uses the reward. And that the value functions are used to modify the policies through learning processes. And the fourth step, which we're about to get to, step 4, would be that we start to have, we build a transition model. We have a predictive knowledge of the world that also takes the state and is used for planning. And by planning, we also adjust the reactive policies. Okay, so let's get to that fourth step. Predictive knowledge. This is how knowledge can be expressed in experiential terms rather than in objective terms. So let's first recognize that much world knowledge, just seems not to be about experience. It seems to be about the world. So when we say Joe Biden is president of the US or the Eiffel Towers in Paris, these are statements very explicitly about the external world. Most birds have wings. Oregon is north of California. The car is 10 meters ahead. Fire engines are red. Maybe that's slightly experiential. Well, let's look at some other knowledge that is more seemingly experiential, because a lot of it is more like that. It's a long walk to the city center. I can lift 200 pounds. It's cold outside today. My spouse is blonde. My foot is sore. Or the 7th pixel will be blue in 3 steps, as we saw earlier. So I just want you to think about the spectrum here and how far it is, how big the gap is from, the 7th pixel will be blue in 3 steps and Joe Biden is president. This is a very large gap, but maybe it's crossable. Is it a gap in qualitatively or quantitatively? Can we imagine crossing it? So going back to history, in the old days, good old-fashioned AI systems, since they didn't have experience, they couldn't predict, they weren't about that. They had facts, they had knowledge in them, would be more like a database. The president of the US is equal to Joe Biden. The capital of France is Paris. And this would be a kind of knowledge that they would typically have. Now, go into more modern times, probabilistic graphical models again, that had knowledge about events. So, cloudy and the sprinkler and the rain, there would be a probability distribution over these events. That would be the knowledge. And there would be relationships between the probability distributions. But it was all about simultaneous events. What's the probability that you will see the grass being wet and also it being raining at the same time? That simultaneous events is not about sequential events. And really, if you're going to talk about prediction, you need to talk about sequential events. Or the gradual transition is that prediction is knowledge with a clearer semantics, and the predictive view of knowledge is becoming more prominent in AI. I would say in machine learning, this predictive model of the world is more or less the modern view. It's not just the new view; it's the standard view of what world knowledge is. And the cutting edge of this predictive knowledge, in my opinion, is the idea of general value functions and option models, which are key ideas that have come out of reinforcement learning. So let me talk some more about knowledge. When I say world knowledge, I don't really mean mathematical knowledge. Mathematical knowledge is true in any world, and thus it's not true. It's not about this world. It's not even about this world. And so I'm not talking about mathematical knowledge. And another division we can make is into knowledge about the state of the world, which we've already talked about. That's the state. And then there's knowledge about state transitions, which is really what we're talking about now. The predictive model of the world is about state transitions. So when you make a state-to-state predictive model, it doesn't have to be low level. Like we might think of it as like physics, like differential equations or like Markov decision processes. And all those seem sort of too low level to deserve the name knowledge. But they don't have to be low level. They can be abstract in space and time. You can have the experiential state could be very abstract. Like you could have a state of being at home, which means you might see certain things and experience certain things. And they can also be abstract in time. So this is the idea of options, in which your predictions can be conditional on entire ways of behaving. And so an option is a policy plus a termination condition. And you can make transition models for options, just as you can for transition models of lower level things. But they're well understood, and you even have algorithms for learning them off policy. So using this technology, we can certainly make predictive models that are not low level. But what are the limits to this? It's not clear, and I just want to claim that it's not clear. Like, how expressive can an option model be? How close can we get to what we might common sense essentially think of as knowledge? And can we possibly bridge this abstraction gap between experience and knowledge? Okay, now I'm just going to wrap up and proselytize a little bit, I guess. Experience is fundamental to world knowledge. You know, by definition, we agents, we gain information about the world through our sensors and affect the world through our actions, through our experience. So we know the world through our experience. Everything we know, in some sense, it seems plain to me that it's a fact about our experience. It seems inescapable. And it's good in the long run. It's good for the science of AI that knowledge should be bound to experience, because that makes it learnable and grounded. But still, you know, we don't like to think about experience. I want to really acknowledge this. So I'm going to put my face on here and speak right to you guys that why is it we dislike experience? Well, experience is because it's strange, it's low level, it's unfamiliar, it's not intuitive, it's complex, it's all those little buzzing lights, colored pixels, and tiny time steps. So it's also hard to talk about. It's subjective. It's private to each of us as individuals. We can't talk to each other about the pixels or the small signals flitting through our sensor organs every 1/10 of a second. So really, these objective terms are superior. Public, external, objective terms, they're clearly superior for everything, really almost everything we do, with a possible exception that maybe for creating AI, we need to think in these other terms. So I want to sympathize with the desire to dislike and avoid experience, and yet perhaps we need to get over that. The reason why should we like experience? Well, experience comes from the ordinary operation of the agent. It's free data. And that way it enables autonomous learning that scales with our computational resources. It offers a path to knowing the world, because any fact about the world is a fact about experience. Then it can be learned and verified from experience. So in sum, I've discussed 4 major steps in the increasing role of experience in AI: agenthood, reward. Those 2 clearly have happened. And then we're starting to take it into state and knowledge. So for each one of these steps, I've shown that AI has chosen first to work in objective, non-experiential terms. That's just our normal inclination. But we've seen that there is a less familiar approach based on experience, and that has important advantages in grounding, learnability, and scaling. This trend towards sensorimotor experience in AI may have farther to go. The 3rd and 4th steps are not complete. There are research opportunities. Ultimately, I think it's quite possible that the story of intelligence might be told in terms of sensorimotor experience. So whenever I give a talk, I like to say everything as simply as I can. And so often I will try to reduce it to a really super simple, maybe 2 simple terms, a slogan. So my slogan for today's talk, if I had to reduce it, I would reduce it like this: that data drives AI, and experience is the ultimate data. Thank you very much for your attention.
Thanks, Rich, for a wonderful talk.
I would be delinquent, Rich, if I didn't ask you a few questions from the good old-fashioned AI point of view. So let me ask a couple to see what you have to say. The first, there's two that I think I can use to frame this. The first one is just a general question about accumulating knowledge or experience by being told versus observing, right? You remember Yogi Berra's famous phrases, you can observe a lot just by watching. But the point is I can tell a child that a particular object is a chair, even if a child doesn't know how to sit down, doesn't matter. They are likely to be able to make predictions about what things are chair-like. And that sort of rolls into the second question, is that it's very hard for me to agree that formal representations don't make predictions. When we use logic or non-monotonic logic, we make predictions based on accumulating things about the world. When we use Bayes' rule, like in your sort of the grass is wet because it's cloudy and the connections, dependencies there, we also make quantifiable predictions, that is probabilistically how accurate they are based on the priors we have, or logically based on the semantics of the logic. So where in what you say could I tell the agent you're talking about that a chair has this property?
Well, yeah, there are many things there. So as I've tried to make it clear, I totally sympathize that for talking to each other, for almost everything we do, we're going to use experiential terms. We have to talk to each other. We have to talk about the external world. We can't talk about our detailed sensory signals. Mm-hmm. I think, though, really, Randy, you should agree with me, at least in the main theme, observation of my talk, because my talk is observational, that this shift has happened. Yep. And you know, just because a trend has been in motion doesn't mean it will continue or it should continue. Right. I think that's a harder thing, yes, to assess. Yeah.
What I see.
So you've talked about the probabilistic graphical models, and we often use the word prediction when we talk about them, but they are about simultaneous events. They're not about sequential events. And really, life is made up of a time series. You know, it's quite explicit when we talk about probabilistic graphical models, right, that it's the primary setting is a timeless setting. And there's
so one of the things that I do agree with the proposition that you're using to explain intelligence, and that is that it includes a significant component of eliciting observations experientially and then figuring out how those actually produce representations that allow us to make those sequential decisions that we're faced with. But I think what I want to do is avoid the misinterpretation to all of the graduate students and maybe some others listening to, is that we can't describe those things in terms that we can interact about in language or in, for example, temporal logics, even the situation calculus from Pat Hayes and James Allen's algebras of time. We can formalize that as required to meet the demands of prediction, right? And so I think maybe what you're saying that I can agree with is that there are different ways of capturing that information. And I agree that we don't have much in the way of technologies to support the exchange of experience in the way you talk about it. So maybe that's TikTok, but so I agree with that. It's just you somehow paint a picture of there being a contrast, and there needn't be a contrast, right? That's all.
Well, there is a shift, and the shift has happened for a reason. The logics are less connected to experience, and that makes them less suited for learning and less suited for scaling with computation. And this is just the big trend in AI. One of the big things we've learned is
Yes.
the rise of machine learning. It's all about the ability to learn these things. And
I agree with that. And one of the early slides that you had, you used the word explanation, and you were using the term about scientific explanation for the phenomena captured and at which level of detail. So that's plausible. That's sensible from a scientific point of view for sure. But now with the another growing interpretation of explainability is that we can't take two models. You know, I've always been a fan of reinforcement learning because you're actually building something explicit like a policy. But if you take two deep learning models and you start to consider how to combine them, which is partly the future of the world, right? Exchanging models, not data somehow. You have to build abstractions that you can debug. So we can take two formal mathematical descriptions, either using Bayes rules or some kind of logic. We can inspect them and use the communication medium to say, oh, these are contradictory here. But like one of our colleagues, Nilanjan Ray, says about deep learned models, we don't know how to explain the fact that a multi-billion parameter deep learned model can be syntactically, surgically remove half the model and still get the same predictive accuracy, for example, or sometimes even better. So that's why I'm an advocate for this full spectrum of capturing experience and using it as appropriate, because remember that you'll know this better than anyone because you said it about scaling before, and scaling is really important if you're learning more complex concepts, but debugging them requires you to have a language to talk about them. Maybe that's the point. Anyway, I've said enough.
We all really feel this tension. We talk about things, we don't want to use experience, and for some needs we're driven to it. We all feel that. Yeah. Thank you, Randy.
No, I agree, and I think that I was semi-serious about TikTok because it was almost 20 years ago when people claimed that we have enough memory and enough sufficient sensory devices to record our whole existence. So if I was to say, oh, I had this conversation with Rich 20 years ago, we could look at the experiential record and say, yes, you did, or no, you didn't, for example. And I think that that's a factor in your promoting this balance of experience for sure. So thank you very much.
Thank you.
Hi, Rich. I also have two questions for you. First one is that you specified that general value functions are kind of best way for predictive knowledge, right?
In one way, yeah.
Yeah, so why do you think it's so?
Oh, well, I would say that they're the only example that we have of an efficient way to predict functions of the future. Like, generally speaking, in the literature, there are many people that talk about prediction, but they're only talking about, it's almost overwhelmingly talking about what the next symbol or the next video frame will be. We need to predict. The notion of prediction is far larger than that. I might, predict that what I will see if I go home, or how long it will take me to walk to a place, or I might predict that if I dropped a feather and a stone, they will fall at a different rate. All these things are much more complicated things, and we need to be able to express those more complicated things. So I talk about, value functions are like an intuition pump because all of us, or many of us, will understand, okay, value functions are familiar. We've looked at them for many years. So maybe we can use similar technology to predict other things. And that's what the idea of a general value function is.
And do you think that predictive knowledge is kind of explainable?
So I do think that maybe we can't really. I mean, the first observation is that people can't really explain their own knowledge to each other. Like we can't explain to each other how we see or how we walk. It's very hard for us to do it. And psychology has found out that when we do provide explanations, they're often not what is the actual reasons why we do something. They're often wrong. They're often, like the mind has a PR agent that's explaining what it's doing, but that's not it's the real reasons why it's doing them. I think explanation is really tough. It would also be really, really useful. I don't really know how to do that. But I guess I'm also saying it's not a first order requirement. The first order requirement is you have to be able to model the world in a way that enables you to predict and control it. And explainability is something additional that we want to add on top of it. Really, I guess it's explainability is we want the mind to work in objective terms, right? Because then it could explain it to us. It could explain itself to us and its choices to us. We want the mind to think in terms of external objective terms. Yeah, and so I sympathize with that, but I also feel the trend towards experience, for good reasons, is drawing us away from that.
Yeah, and in fact, what you say, what Shaheen is asking is back to your original use of explanation in your slides, is that scientific explanation is about providing a path of understanding to reproducibility or causality. But in everyday general life, when I explain to you what I did as an event, interaction with the environment, my explanation may bear no causal relationship to that thing. And so I think you're right about that. But I think that ultimately, when we interact with each other, for example, as scientists, we're in pursuit of the causal explanations to base our understanding and future sort of scientific progress. So I think there is at least that spectrum. Again, thanks for indulging us.
So do I have any more comments or questions?
There is one comment from Greg Konrak in the chat box. He says, knowledge comes from experience, experience comes from bad judgment.
Knowledge comes from experience and
experience comes from bad judgment.
Bad judgment.
Any other questions?
Well, thanks everybody.
Thanks.
Okay, here is one question. So you talked about reward as being another signal among the other agent state signals. I am thinking whether we can take the reward signal formally as part of the agent state then as well. Is the expected difference between what the prediction of the agent state and what it actually is enough in simpler terms?
Yeah, well, there's probably several questions mixed in there. So yeah, formally, the reward is part of the sensation because it's information we receive from the world. And so it's some information we receive that might lead us to form a state representation and be part of the way we form it. And that's certainly true. And I think there are TD methods for updating that as well. I think that also intuition is probably sensible. Okay, thanks a lot, everybody, for today. And I hope you all have a good rest of the day. Thank you for your attention.
Thank you. Thank you for presenting today. Thank you everyone for joining in. See you next week, everyone.
Bye-bye.